Hi, my name is Sebastian, and today I'm going to be talking about my project, which is camera shake deconvolution using motion sensors. So the problem that my project addresses is the problem of blind deconvolution. So we know we can model a blurry image as a convolution of the original image with a blur kernel and some noise. So if we're given a blurry image, the problem is how can we find the blur kernel and the original unblurred image? The problem with blind deconvolution is that there's often not enough constraints on the problem, so it makes it very challenging. Now, since blind deconvolution is so challenging, I thought maybe we can make it easier by adding some sensors to estimate the camera's motion throughout an exposure. So my solution was to add gyroscopes. I added 3-axis gyroscope. So the setup is shown on the left. We see the breakout module with the 3-axis gyroscope connected to an Arduino board, and then that's all glued onto a cardboard plane, and the camera is then attached to that plane. Now on the right here we have the blurred image that we're going to process throughout the rest of the presentation. Now we have a new problem. We have the gyroscope data, and we know that gyroscopes measure angular velocity, so we can integrate this angular velocity data in order to get the relative angular position, and then from here we can generate rotation matrices. So now that we have rotation matrices, it becomes a lot easier to find the camera movement. And we can do this by using planar homography. So here's the equation that is used. Note that we're eliminating translation to simplify the problem a bit, and also because the majority of camera shake is mostly due to rotation anyway. All right, so now we have a point trajectory for each time k, and how can we estimate a PSF from this? So unfortunately, gyroscope data is like pretty noisy, and so we want to eliminate a lot of that noise in order to get the most accurate PSF possible. As seen on the left graph here, we can see that like the noise is pretty approximately a distributed Gaussian. So we can weigh each point in the PSF according to this Gaussian distribution. Now we get this equation on the right where F1 and F2 are the Gaussian distributions for each axis. And here's the result of estimating the PSF. The left image shows a general trajectory estimated by the motion sensors, and then on the right we have our estimated PSF. And honestly, it's not bad at all. I think it's actually very accurate. Here, the true blur kernel is shown at the bottom image here, and honestly, they look very similar. Now that we have the blur kernel, we can use non-blind deconvolution in order to extract the unblurred image. And so this non-blind deconvolution becomes a lot easier. Now we can use a classical method, which is Richardson-Lucy. Pretty much this is an iterative algorithm that is going to maximize the maximum likelihood estimator of a Poisson image statistic according to this time step here. Now the problem with Richardson-Lucy is that it causes a lot of ringing. You can see this image on the right has a lot of artifacts and a lot of ringing. So this is in part due to high contrast edges. So we can introduce a gain scaler to sort of mitigate this. And so our new update step is going to be this update step, which is the original update step times a gain constant. And the result on the right kind of shows our output. It definitely looks a lot better, definitely less artifacting and less ringing. On to some results. So here's the original image that we were processing. After applying the blur kernel, we get this result over here on the right, which definitely a lot sharper than the original image. I would say it's a good result, not a lot of artifacting. But yeah, on to the next result. We have a rockfish textbook, which is very blurry. The authors are not discernible in the left image, but after applying the PSF, we get the right image where a lot of the text on the textbook is actually very readable. So I would say this is honestly a successful result, despite the ringing that is prevalent on the left side of the image and on some of the edges. Now, finally, we have probably the worst result of the three. So the PSF is applied, and then we get the right image, which has just too many artifacts, I think. Even though it's slightly sharper, I would say the artifacts definitely ruin this image. So yeah, I think that this algorithm could definitely be used in the real world, especially considering that like most phones nowadays have gyroscopes built in. So with some refinement, I think that this could be a very useful algorithm.